Hi student, this is Ajay Kumar working as a ED and NEET faculty. So in this video I would like to discuss about a simple concept called hyperconjugation. We will see what is the definition of hyperconjugation and what kind of carbon compounds exhibits hyperconjugation. We are also going to see some application questions from the concept. Okay, so let me define what is meant by hyperconjugation. Okay, so already I kept here the heading hyperconjugation. So let me give the definition like this. So polarization of alpha CH bonds at sp3 carbon next to the sp2 carbon is known as hyperconjugation. So let me repeat once again. Polarization of alpha CH bonds at sp3 carbon next to the sp2 carbon is known as hyperconjugation. So I can also write on the board here polarization of alpha CH bonds at sp3 carbon next to the sp2 carbon is known as hyperconjugation. So the definition looks a little tricky, but it is very simple to understand. So polarization of alpha CH bonds at sp3 carbon next to the sp2 carbon is known as hyperconjugation. Okay, so there is the theoretical definition of hyperconjugation. So what are the conditions to show hyperconjugation effect? So what are the conditions? You must have sp3 carbon and you should have sp2 carbon. Okay, so sp2 carbon must be there, sp3 carbon must be there. Also, you should have alpha CH bonds at sp3 carbon. In general, alkenes, carbocations and free radicals undergoes hyperconjugation effect. Okay, so let's start with first alkenes. I will take one example alkene, then I will describe how the hyperconjugation effect undergoes. Okay, so let me take a simple molecule like propene. I will take propene molecule and explain everything. Okay, so propene, what is the chemical formula? The propene, this one, CH2, CH3, CH double bond, CH2. This is propene molecule. In order to understand little bit clear, I would elaborate the structure and write like this. I can write propene like this. So this is I have written like this. So in order to understand little bit clear. Okay, so I have written like this. What are the conditions for the hyperconjugation? In order to exhibit the hyperconjugation, what are the conditions? What are the definition given? So sp2 carbon must be there. Okay, this is sp2 carbon, this is sp2 carbon. So generally, if carbon makes double bond means, then the carbon hybridization would be sp2. Okay, sp2 is there. After sp2, immediately next you should have sp3. So sp2 carbon is there, immediately we have sp3 carbon also there. Okay, so that sp3 carbon only is known as alpha carbon. Now they said alpha CH bond. The bonds present at alpha carbon is called as alpha CH bond. See, this is the CH bond. So this is the alpha carbon. The bonds here given are called as alpha CH bond. So all the conditions are fulfilled to show hyperconjugation effect. Okay, so we have sp2 carbon and immediately you have sp3 carbon. At sp3 carbon you have CH bond. Now polarization of bond will take place. How the polarization of bond will take place? See, this bond will polarize here. So actually what is mean by polarization? Polarization means movement of bond or separation of charges. Movement of bond or separation of charge is called as polarization. Now, the sigma bond present between carbon and hydrogen will move from here to here. Consequently, this pi bond will move toward this carbon. As a result of that, you will get a structure like this. Yeah, this is the structure we get. Now here, this bond is becoming bond between these two carbons. Okay. So then what would happen? This pi bond will polarize toward the carbon. Consequently, you will get one hyperconjugative structure like this. This is called hyperconjugative structure. Hyperconjugative structure. Here what happens? See, the hydrogen, this hydrogen remains like H plus because there is no bond between these two atoms, and the completely bond is shifted from here to here. So now hydrogen stays without any bond there. Okay. So and since hydrogen is not having any electron, it will carry a positive charge. Next, the carbon, the pi bond is shifted towards the carbon. Then the carbon will take up a negative charge like this. Okay. So since we don't have any bond between this carbon and hydrogen, hyperconjugation is also known as no bond resonance. No bond resonance. Hyperconjugation is also known as no bond resonance because you don't find any bond between that hydrogen and carbon in hyperconjugative structure. That's why hyperconjugation is also known as no bond resonance. Okay, and this is one hyperconjugative structure. But how many hyperconjugative structures we will get for this molecule? It depends on number of alpha CH bonds at this sp3 carbon. sp3 carbon. That sp3 carbon, alpha carbon, both are same only. So number of hyperconjugated structures depends on number of CH bonds at sp3 carbon. Okay, here how many we have? This is one, this is one, this is one. We have 3 CH bonds at alpha carbon or sp3 carbon. Got it? So we should get now 3 hyperconjugated structures. So this is one. If you use this bond, you will get this hyperconjugated structure. You can also use this one, or you can also use this one. So I will write one more structure, hyperconjugated structure. You keep this hydrogen stable and use this hydrogen for the polarization. Then you will get one more hyperconjugate structure like this. Now what we will do is, you keep these two hydrogens stable and use this hydrogen bond for the carbon hydrogen bond for the polarization of the bond. Carbon bond. Yeah. So how many hyperconjugated structures we got? 1, 2, 3. So for propene molecule, we got 3 hyperconjugated structures. So number of hyperconjugated structures equal to number of CH bonds present at sp3 carbon or alpha carbon. Okay. So this is the alpha carbon. We have 3 CH bonds. This is one, this is one, this is one. With this we can write one hyperconjugated structure. With this bond you can write one hyperconjugated structure, and with this bond we can write one more hyperconjugated structure. So all together we will get 3 hyperconjugated structures. So 1, 2, 3. 1, 2, 3. Okay. So what is the use of these hyperconjugated structures for alkenes? So I have taken an alkene. I have explained about hyperconjugation. So what is the application of hyperconjugative structures? Okay. So the mainly hyperconjugative structures or the concept will be useful to understand the stability of alkenes. Stability of alkenes. Okay. Higher the hyperconjugated structures, higher will be the stability. Always the stability of alkene is directly proportional to the number of hyperconjugated structures. Okay, that is a small trick you should understand. You should understand. So because in case of IIT JEE exams and NEET exams, the questions keep on comes. If you look at previous question papers, IIT JEE question papers from hyperconjugation, the question is given: which of the following alkene is more stable? In order to understand the stability of alkenes, you should know number of hyperconjugated structures. Number of hyperconjugated structures. So stability of alkene is directly proportional to stability of alkene is directly proportional to number of hyperconjugative structures. Number of hyperconjugative structures. Simply, I will label as NHS. NHS means number of hyperconjugative structures. Okay. So stability of alkene directly proportional to number of hyperconjugated structures. Now I would give one example to solve. So let us see how the stability of alkenes varies. So I will give option A. I will give CH3 CH double bond CH2. Option B, I will give CH double bond CH CH3 CH3. Okay, so this is one alkene, this is second alkene. Now I will give two more options. So let me take CH3 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 H, and here CH3 CH3. Yeah. So now I have given here four molecules, all are alkenes. Since we have double bond between two carbon atoms, so these are alkenes. All are alkenes, but all alkenes are not same. This is different, that is different. All are different alkenes because the substitutions are different. Around carbon, the substituted groups are different. So I have given different four alkenes. Now among these all alkenes, which one is more stable? Which one is more stable? I told you, right? The stability of alkene is directly proportional to the number of hyperconjugated structures, NHS. Number of hyperconjugated structures, NHS. Understood? So let us see here. Just now we have seen number of hyperconjugated structures for the propane. Okay. So how many number of hyperconjugated structures for this molecule? Okay. Already we have seen, right? So there is a sp2 carbon. In case of propane, sp2 carbon is there. After sp2 carbon, immediately you should have a sp3 carbon. At sp3, you should have hydrogen. Okay, so number of hyperconjugated structures equal to number of CH bonds at sp3 carbon. So here how many CH bonds will be there? 3 hydrogens. With 3 hydrogens, carbon makes 3 bonds. So 3 CH bonds are there. Since we have 3 CH bonds at alpha sp3 carbon, number of hyperconjugated structures would be 3. Number of hyperconjugated structures would be 3. Fine. So now let us see here. Here how many hyperconjugated structures you will get? Look at here. This is sp2 carbon. This is also sp2 carbon. Okay. So beside sp2 you have sp3. This side also beside sp2 you have sp3. So this is also labeled as alpha carbon. This is also labeled as alpha carbon. Alpha carbon, that means which is directly attached to the sp2 carbon. So this is also can be labeled alpha as well as this one. So both are alpha carbons and both carbons undergoes sp3 hybridization and both carbons carries hydrogens. Here you have how many hydrogens? 3. Here how many hydrogens? 3. You have total 6 CH bonds. Then you will get number of hyperconjugated structures 6 here. 6 here. So let us come down here and count number of hyperconjugated structures here. We don't have to write number of structures on the bond. If you know the number of CH bonds at alpha carbon, simply you can count or you can write number of hyperconjugate structures. Okay, so again this is sp2 carbon. Beside sp2 carbon you have sp3. Of course this is also sp3, this is also sp3. This is also alpha carbon, this is also alpha carbon, because both are directly attached to the sp2 carbon. Got it? Next, so let us take this one, SCH3 carbon. So this CH3 is again directly connected to the sp2 carbon. So how many alpha carbons? We have 1, 2, 3. And each alpha carbon is also undergoes sp3 hybridization. And the carbon carries, each carbon carries 3 hydrogens. This one 3, this one 3, this one 3. Total how many alpha CH bonds we have? 9 alpha CH bonds we have. 9 alpha CH bonds we have. Then number of hyperconjugate structures NHS equal to 9 here. 9 here. So let us go right side. So let us look at now this molecule. This molecule. So sp2 carbons are there. So this is sp2 carbon. Directly sp2 carbon connected with sp3 carbons. And sp3 carbons we have hydrogens also. This one also look at here. This is the sp2 carbon. So this sp2 directly connected to sp3 carbon. And again here at sp3 carbons we have CH bonds. CH bonds. We have here 4 alpha carbons. 4 alpha carbons, and 4 alpha carbons are undergoing sp3 hybridization. Moreover, each carbon carries hydrogens. Here this is carrying 3 hydrogens, 3, total 4 into 3. 12 alpha CH bonds we have. 12 alpha CH bonds. Then number of hyperconjugation conjugate structures equal to 12. We can also write number of hyperconjugate structures one by one on the board or the paper. But that is not going to help us in competitive exams. Just you have to look at the molecule and count number of hydrogens, number of alpha CH bonds at alpha carbon, and find out number of hyperconjugate structures. Okay. Higher the hyperconjugate structures, higher will be the stability. That is what this is a kind of trick actually. What is the trick? So stability of alkene is directly proportional to number of hyperconjugate structures. Number of hyperconjugate structures. Okay. So then among these 4 options, which is more stable? Option D. Option D. Option D is more stable. If you want to arrange them in the increasing order of stability, first D will come, because D is having more hyperconjugate structures, 12 hyperconjugate structures. Then C will come. So D is more stable. Then alkene C is stable. Then alkene B is stable. The least stable goes to option A. Option A. So option A, propane is least stable because it is having less number of hyperconjugate structures. So option D is more stable. This alkene is more stable because it is having 12 hyperconjugate structures. So this is how the questions will be posed upon the student. Okay, so let me give one more example. Let me give one more example. I will take alkene like CH3. So let us label this one as A, and I will give one more. This one H. Okay. See, so look at these 2 alkenes and find out which is more stable. Which is more stable. Again, we have to understand according to number of hyperconjugation structures. Number of hyperconjugate structures. Okay, so look at here. How many hyperconjugate structures are possible for this one? So sp2 carbon connected with sp3 carbon, and sp3 carbon having 3 CH bonds. This side you have 3 CH bonds. This side you have 3 CH bonds. It will produce 6 hyperconjugate structures. So number of hyperconjugate structures equal to 6. Here how many hyperconjugate structures you will get? Here also same only, because here also like this 2 CH3 groups are there. Here also we have Two CH3 groups are there. So here also you will get hyperconjugated structure 6 only. 6 only, because here you have 6 alpha CH bonds. Here also you have 6 alpha CH bonds. Okay. So same number of hyperconjugated structures. So in order to understand the stability of these compounds, we cannot apply hyperconjugation now. So the stability of these two alkenes cannot be explained based on the number of hyperconjugated structures, because number of structures for both compounds same. Then how you will decide? So you look at the structure. This is cis alkene. Cis alkene. When same kind of groups are oriented in the same side, we will say that alkene as cis alkene. If same kind of groups are oriented in the opposite direction, then the alkene is labeled as trans alkene. Trans alkene. In general, trans alkenes are more stable, because the groups are, the bulky groups are opposite to each other. Here bulky groups are close to each other. Here in cis alkene more repulsions will be there. In trans alkenes less repulsions will be there. So therefore trans would be more stable. Trans would be more stable. So here the stability of alkene we did not explain based on hyperconjugated structures. We explained based on position of the groups present around the double bond. In general, cis alkenes are less stable, because cis alkenes creates more repulsion within the molecule, whereas trans alkene will reduce the repulsions. So therefore trans alkenes are more stable. Got it? Yeah. So this is the hyperconjugation. Hyperconjugation concept. So based on hyperconjugation, we explain stability of alkenes. Sometimes if you don't explain stability based on number of hyperconjugated structures, we have to explain cis and trans concept. Based on cis and trans concept, we have to explain the stability. Understand? So I also give one more example. To understand hyperconjugation effect, or I will give one more application questions to understand the stability of hyperconjugation structures. Okay, so look at here. I will give again 4 options. CH2 double bond CH2. Option B, CH3 bond CH double bond CH2. This is one alkene. Option C, I will give like H CH3 CH3. CH3 CH3 CH3. Yeah. So now based on hyperconjugation, we know that how we can explain the stability. Now based on the stability, we explain heat of hydrogenation. We explain heat of hydrogenation. Heat of hydrogenation. So delta H. Heat of hydrogenation delta H. So what is mean by heat of hydrogenation? The amount of heat released. The amount of heat released when an alkene undergoes reduction. We know that alkenes and alkanes undergoes reduction reaction and becomes alkanes. Okay. So when an alkene undergoing reduction reaction or hydrogenation reaction, how much amount of heat is released? That amount of heat is called heat of hydrogenation. Heat of hydrogenation. Now what the question is, which of the following alkene has highest heat of hydrogenation? Highest heat of hydrogenation. In order to understand the highest heat of hydrogenation, first you should know the stability. And stability and heat of hydrogenation both are mutually connected. So this is the previous question. So they have given 4 options like this, and they were asking, so which of the following alkene will have more heat of hydrogenation? More heat of hydrogenation. What is heat of hydrogenation? The amount of heat released when hydrogenation reaction occurs. occurs. So I will give a small trick to understand. Heat of hydrogenation is delta H, right? So heat of hydrogenation delta H is inversely proportional to the stability of alkene. Stability of alkene. Heat of hydrogenation delta H is inversely proportional to the stability of an alkene. If alkene is more stable, then heat of hydrogenation would be less. If alkene is least stable, then heat of hydrogenation will be more. This is a simple trick you remember, then you can easily answer in JEE exams. Okay, so first you should able to understand the stability. If you are able to understand the stability, automatically you will understand heat of hydrogenation. Got it? Again, how you will understand the stability? Again, depending on the number of hyperconjugated structures. Higher number of hyperconjugated structures, higher will be the stability of that corresponding alkene. So how many hyperconjugated structures here for option A? So option A, you have sp2 carbon. There is no sp3 carbon. If you don't have sp3 carbon, no need to expect any hyperconjugated structures. So number of hyperconjugated structures here 0. There is no alpha carbon or sp3 carbon, and there is no hydrogen at alpha carbon. Therefore, number of hyperconjugated structures equal to 0 here. So let us come down here. Let us go there and see how many hyperconjugated structures. Already we have seen for this molecule 3 hyperconjugated structures. So this is an example already we have discussed earlier. So how many hyperconjugated structures here? Just now we have seen number of hyperconjugated structures 6, because so 2 alpha carbons are there. Each alpha carbon carries 3 hydrogens. Total number of alpha CH bonds 6. So number of alpha CH bonds are 6. Then number of hyperconjugated structures 6. Fine. Now here how many number of hyperconjugated structures? Number of hyperconjugated structures. So number of alpha CH bond how many? 3. So total we have 12. Understand? So this is having 12 hyperconjugated structures. Therefore, this is more stable. This is more stable. If this is more stable, the heat of hydrogenation of this alkene will be very, very less. That is what the trick, right? Heat of hydrogenation is inversely proportional to the stability of an alkene. If alkene is more stable, heat of hydrogenation would be less. But what is the question I have given? The question is, which of the following alkene is having more heat of hydrogenation? Or which of the following alkene having highest heat of hydrogenation? Okay, so this is having 6, this is having 12, this is having 3. Here there is no hyperconjugated structures. So that means among all these 4 alkenes, the alkene A is least stable. Least stable means then heat of hydrogenation would be more. So alkene A is the answer. So alkene A is having highest heat of hydrogenation. When hydrogenation happens, more heat released in this case. This is also a previous question given in the IIT JEE exam. Okay. Yeah. So this is about applications about hyperconjugation and definition. Okay. So till now we have seen hyperconjugation in alkenes. Okay, so even carbocations and radicals also undergoes hyperconjugation. Condition is same. Whatever definition I have given in the beginning, same definition. You must have a sp2 carbon, and immediately after sp2 you should have sp3 carbon. At sp3 carbon you should have CH bonds. The condition is same. Whether you take alkene or radical or carbocation, whatever organic species you take, a definition is same. Definition of hyperconjugation is same. Fine. So now I will take carbocations. So carbon carrying positive charge is called carbocation. So I think everybody knows about that. So carbon carrying positive charge is called carbocation. So now I will give some examples of carbocation, and for those compounds we can write hyperconjugated structures. So suppose let me take CH3, CH3, CH2 plus. It is a carbocation. It is a carbocation. So does it show hyperconjugation or not? That is the question here. Again, we have to go back to the definition. You should have sp2 carbon. Do you have sp2 carbon or not? So carbon, positively charged carbon is always sp2 carbon. So this is the sp2 carbon. Okay. So sp2 carbon is there. And beside sp2 carbon, you should have sp3 carbon. sp3 carbon is there. This is sp3. And this is sp3 carbon. That sp3 carbon only called as alpha carbon. Okay, so sp2 carbon is there. Immediately you have sp3 carbon. That carbon only called as alpha carbon. Okay, and at sp3 carbon you should have a CH bonds. CH bonds are there. So all conditions are fulfilled to show hyperconjugation. sp2 carbon is there, sp3 is there. At sp3 you have CH bonds. Then it will show hyperconjugation like this. What is hyperconjugation? Polarization of bond, right? What will happen? Polarization of bond. Polarization means movement of bond or separation of charges. So the bond, this bond will move here. This bond will move here. Then you will get since this hydrogen losing this bond, the hydrogen will take a positive charge like this. Like this, and this sigma bond becomes pi bond between these two carbons in this structure, and this is the symbol for hyperconjugation. Okay, fine, that's it. So then how many hyperconjugated structures we get? Number of hyperconjugated structures again depends on number of CH bonds at sp3 carbon or alpha carbon. How many bonds we have? 1, 2, 3. So same we will get. So with this hydrogen, one hyperconjugated structure. With this hydrogen, one more. And with this also you can write. So let us keep these two hydrogens stable and let us polarize this bond. C double bond CH. No bond. Yes. Okay. So since we have 3 CH bonds, we will get 3 hyperconjugated structures. 3 hyperconjugated structures. Simple. So carbocations also will show hyperconjugation. But you must have sp2 at sp2 should be connected with sp3. At sp3 carbon you should have CH bonds. CH bonds. Okay. So you take any carbocation. So you can take any carbocation, we can write number of hyperconjugated structures. Okay. So now, based on this, let me give one example to understand the stability of carbocations. See, hyperconjugation is useful to understand the stability of alkenes and hydrogenation or heat of hydrogenation of alkenes. And now we are also going to understand the stability of carbocations by using hyperconjugation. Okay, that's it. So you got it. Yeah. Again, stability of hyperconjugation. Stability of carbocation. Stability of carbocation. Again, inversely directly proportional to the number of hyperconjugated structures. Stability of carbocation is directly proportional to the number of hyperconjugated structures. Shortcut I have written NHS. That means number of hyperconjugated structures. So let me take 4 examples. This is one carbocation. Let us label this one as A. And let me take one more carbocation like CH3, CH2 plus. This is second carbocation. Let us label this one as B, and let us take one more carbocation CH3, CH3 plus. Okay, so let us, okay, we can take 3 carbocations. So which is more stable? which is more stable. Okay, so do we have here hyperconjugated structures? How many hyperconjugated structures we have? We have sp2 carbon. Beside sp2 carbon, you don't have any sp3. If you don't have any sp3 carbon, no need to expect any hyperconjugated structures. There is no hyperconjugated structures. Let us come here. So there is sp2 carbon is there. Positive charge always will undergo sp2 hybridization. So sp2 carbon is there. sp2 carbon, beside sp2 we have sp3, and sp3 have 3 CH bonds. Therefore, number of hyperconjugated structures equal to 3. Got it. So let us go there. So here how many? So sp2 carbon is there. This is also sp3, this is also sp3. Both are alpha carbons, both are sp3 carbons. And each sp3 carbon carries 3 hydrogens. This side 3 hydrogens, this side 3 hydrogens. Total we have 6 alpha CH bonds. Then number of hyperconjugated structures equal to 6. Then which is most stable alkene? Sorry, which is most stable carbocation? This one. Because it is having more number of hyperconjugated structures. Got it? That's it. So I can also take one more example to understand furthermore. So let me take CH3, yeah, H plus CH3 CH3 plus yeah, look at here. So I have taken 3 examples. Again, let us label them as 1, 2 and 3. So which is more stable? So all are carbocations because here carbon carries positive charge. Positive charge. Which carbocation is more stable? Again the same concept what I have discussed before. So if you have more number of hyperconjugated structures, the stability of carbocation would be more stable. Okay, yes, fine. So how many hyperconjugated structures? sp2 carbon is there. At sp2 carbon you have 2 CH3 groups. At 2 CH3 groups undergo, this is alpha carbon, sp3 carbon, this is also alpha carbon, sp3 carbon, and both carbons undergoes hyperconjugation because these are directly attached to the sp2 carbon. Then how many hyperconjugated structures you will get? Here you have 3 CH bonds, here you have 3 CH bonds. Then number of hyperconjugated structures equal to 6. Here how many? So you have 3 alpha carbon which is directly connected to the sp2 carbon, and each carbon carries 3 hydrogens. So since we have 3 alpha carbons, total 9 alpha CH bonds, then total number of hyperconjugated structures equal to 9. So let us come here. This total part is called tertiary butyl group. This is one tertiary butyl, this is one tertiary butyl, this is one tertiary butyl. So what are the conditions for hyperconjugation? You should have sp2 carbon. Yeah, we have sp2 carbon, and sp3 carbon must be there. Yeah, we have sp3 carbons also there. So this is sp3, this is sp3, this carbon also sp3. Okay, but at sp3 carbon you should have hydrogen. So this is sp3 and this is not a hydrogen. Instead of having hydrogen you have CH3 groups. We have CH3 groups, right? Then number of hyperconjugated structures 0. So you have CH3 group. So you have sp3 carbons. You have alpha carbon, sp3 carbon are same. You have alpha carbons are there, and all alpha carbons undergoes sp3 hybridization. But at sp3 that alpha carbon is not carrying any hydrogen. You don't have any hydrogen. If you don't have any hydrogen, that doesn't give any hyperconjugated structure. So number of hyperconjugated structures are 0. Now which is more stable? When you look at all these structures, which is more stable? This is more stable. Second is more stable. Then first one, the least stability goes to third. So this is the stability decreasing order. stability decreasing order. So this is how. This is also a previous question given in JEE exam. JEE exam. So carbocations will show hyperconjugation. So hyperconjugation explains stability of carbocations. Fine. Okay. And one more thing. Free radicals also will show hyperconjugation. Free radicals also will show hyperconjugation. So what is mean by free radical? What is mean by free radical? A carbon species which is carrying a single electron is called as free radical. We will represent free radicals like this. It is a carbon species carrying a single electron. One dot equal to one electron. So this is CH3 radical, CH2 radical, CH3 radical. So any carbon species which carries a single electron is called free radical. Generally free radicals are highly reactive. Even free radicals also undergoes and show hyperconjugation. Hyperconjugation. Okay. So suppose, let me explain, let me take one example here. CH3. Yeah, this is ethyl free radical, CH3 CH2. So ethyl free radical. So here carbon carrying a single electron. Okay, so let us see whether it is undergoing, whether it will show hyperconjugation or not. So same definition for this also. What is the definition for hyperconjugation? You should have sp2 carbon. Beside sp2, sp3 carbon must be there. At sp3 carbon, you should have CH bonds. So this is sp2, beside sp2 you have sp3, at sp3 you have CH bonds. So that means all conditions are fulfilled to show hyperconjugation. Hyperconjugation. Then polarization of bond happens. This bond will polarize like this. Polarize and gives this kind of structure. Again, there is the radical, no? So this bond will split into two radicals. One bond equal to two electrons. Radical means one electron, right? So this bond equal to two electrons. One electron will participate in the bond, here pi bond formation. Already this carbon is carrying one electron. Now this bond will give one electron for this carbon. So that electron, this electron makes one pi bond. Okay, and this hydrogen carries one single electron. So this is one hyperconjugated structures. If you write with this one, you will get one structure. So we can also write with this hydrogen and this hydrogen. Then you will get three hyperconjugated structures. Yeah, remove this. Okay, this is second hyperconjugated structure for that free radical. Now one more you can write. So let us write with this hydrogen. Then you get like this. So number of hyperconjugate structures always equal to number of CH bonds at alpha position or at sp3 carbon. So this is the sp3 carbon or alpha carbon. So at this, how many CH bonds we have? 1, 2, 3. So you will get three hyperconjugated structures. Three hyperconjugated. So free radicals also exhibit hyperconjugation effect. The stability of radicals also can be explained by using the same concept. As we explained, the stability of carbocations and alkenes, the same manner we can also explain stability of free radicals by using hyperconjugated structures. Okay, so number of hyperconjugated structures explains stability of free radical. Stability of free radical is directly proportional to number of hyperconjugated structures. Stability of free radical is directly proportional to number of hyperconjugated structures, NHS. Okay, so same thing will take. Instead of positive charge, you take radical. Same examples I have taken. which we have taken earlier. Okay, so these are now radicals. 3 radicals I have taken. So number of hyperconjugated structures again equal to number of alpha CH bonds at alpha carbon. At alpha carbon. Okay, here how many? 6 hyperconjugation structures. Here 9 hyperconjugated structures. Here 0. Because you don't have any alpha CH bond. You have alpha CCH3. There is no alpha CH bond. Okay. So again the stability, same stability order for free radicals also. So second one is more stable and first one, then least stable goes to stability, decreasing order of stability of given free radicals. That is all. Okay. So far what we have discussed is we have seen the definition of hyperconjugation. Then we have seen alkene stability. How we can understand alkene stability by using number of hyperconjugated structures. We also seen heat of hydrogenation. Heat of hydrogenation explained in terms of stability of alkenes. If you know the stability of alkenes, you can understand the heat of hydrogenation, isn't it? We also seen hyperconjugation in carbocations. And we discussed and demonstrated about stability of carbocations. So we also manifested stability of free radicals. Okay. So this is about hyperconjugation and applications. Okay. So I have explained some questions which they have given in previous JE exams. I hope you understood. Okay. So do well. So better luck for your exams. Thank you.